Have you ever felt like you're just guessing your way through life? Well, what if I told you there's a secret language that governs everything, from a simple coin toss to the ups and downs of the stock market? It's the language of probability. And today, we're going to crack the code on a really crucial part of it, figuring out when the past actually matters and when it's completely irrelevant. Okay, let's get into it. So, let's just kick things off with a question that gets right to the heart of what we're talking about today. Imagine a family already has a son. Does that fact change the odds for their next child? Is it more likely to be a girl now or maybe another boy? It's a question that's honestly stumped people for a long, long time. But I promise, by the end of this, you'll see the answer clearly.
All right, to solve this little puzzle, we're going to put on our detective hats. We're going to investigate the cases of two very different families, and each one is facing its own unique probability challenge.
Okay, first up, let's meet the Archers. They're at the very beginning of their journey, planning their family, and they're just curious, what are the chances of having 3 boys, one after another? They don't have any kids yet, so what we're really looking at is the probability of a specific sequence of 3 events that haven't happened yet.
Now this is where it gets cool. This tree diagram lets us see every single possible future for the Archer family. You can see there are 8 different ways this could all play out, and every single one of them is just as likely as the next. But look closely. Out of all those possibilities, only one of them is boy, boy, boy.
So, there you have it. The bottom line for the Archers is that their probability is 1 in 8, which comes out to 12.5%. That's the chance of that whole 3-part story happening exactly as planned right from the very start. But what if we change the story just a little bit? Let's bring in the Burnell family. Now, their situation has a really important twist. They already have 2 sons. So those first 2 events, they're already in the history books. We are only asking about the probability of the next single event. And the answer for them, it's a simple 1/2 or 50%. So wait a second, why the huge difference between 12.5% and 50%? Well, it's because the gender of those first 2 children has absolutely no impact on the gender of the third. Each birth is like a brand new, fresh roll of the dice.
And that situation with the Burnell family, it's the perfect example of our very first key concept today. We call these independent events. You can think of them as events that have absolutely no memory of what came before them.
So here's the official definition. When events are independent, the past doesn't change the odds for the future. This is so important because it helps us avoid things like the gambler's fallacy. That's the mistaken belief that if you flip a coin and get heads 5 times in a row, tails is somehow due. It's not. The coin doesn't remember anything. The very next flip is still and always will be 50-50.
Here's another way to picture it. Olivia has a few highlighters. She picks one out, maybe does some highlighting, but then, and this is the most important part, she puts it back. This is what we call sampling with replacement. Because that highlighter goes right back into the mix, the odds for her second pick are exactly the same as they were for her first. The 2 picks are totally independent of each other.
Okay, but what if the past does affect the future? Let's move on to our next section, where we're going to explore a completely different kind of probability puzzle.
This brings us to the exact opposite idea, dependent events. In these situations, the outcome of the first event actually changes the whole landscape. It alters the odds for the next one. Here, the past matters a lot.
Let's use a really simple example to see what this looks like. You've got a bag with 4 checkers inside, 2 red, 2 black. You draw one out, but here's the game changer. You don't put it back. This one little change fundamentally alters the entire situation for your second draw.
Okay, so let's see how this plays out. On your first draw, your chance of grabbing a red checker is 2 out of 4, right? 50%. But let's say you do it, you pull out a red checker and you keep it. Now look at the bag for your second draw. There are only 3 checkers left in there, and only one of them is red. Your odds just plummeted from 50% down to 1 in 3. The second event depended entirely on what happened first. And think about it, if you'd drawn a black one first, your odds of getting a red would have jumped up to 2 in 3. See? The past matters.
So let's just boil it all down. For independent events, the past has no effect. Think about flipping a coin or drawing that highlighter with replacement. For dependent events, the past changes the future odds. Think about drawing cards from a deck, or our checker example where you draw without replacement.
Okay, so now we get the concepts, which is great. But now let's actually look at the super simple math behind them so you can start calculating these odds for yourself.
For independent events, the formula is about as easy as it gets. To find the probability of both event A and event B happening one after another, you literally just multiply their individual probabilities together. Nice and simple.
Now for dependent events, we have to add one little step to account for how the first event changes the odds. We do this with something called conditional probability. Now, I know that sounds a little technical, but the idea is actually really straightforward. You just multiply the probability of the first event by the new, adjusted probability of the second one.
And that's all conditional probability really is. It's just asking the question, what's the probability of event B happening now that we know event A has already happened? In our checker example, that 1 in 3 chance of drawing a second red checker, that was a conditional probability.
All right, we've got the theory down pat. Now, let's see how these concepts play out in a real-world business scenario where understanding this stuff can be worth millions of dollars.
Let's take a look at a telemarketing company. They're analyzing data from 1,000 calls they made. They really want to understand their true success rate, and this is a perfect real-world case of dependent events in action.
So first, they figure out a baseline. They find that only 16% of people who even answer the phone will stay on the line for at least 1 minute. That's our first event. Let's call it event A.
Now here comes the critical dependency. A sale can only happen if the person actually stays on the line, right? And the data shows that of the people who stay on the line, 10% will actually buy something. That is our conditional probability.
So the big question is, when you combine these two probabilities, how many sales did the company actually make from those 1,000 initial phone calls?
And the answer is just 16. Let's walk through it real quick. You start with 1,000 calls. We know 16% of those people, which is 160, will stay on the line. Then, of those 160 people, 10% will make a purchase. And 10% of 160 is 16. That's the power of combining these dependent probabilities.
You know, understanding the difference between independent and dependent events is just a powerful tool for thinking more clearly about the world around you. So the next time you face a choice, just ask yourself, is this a fresh coin toss? Or is the path I'm about to take shaped by the step I just took? The answer? Well, it might just surprise you.